All right, good morning. Welcome to week 9 out of 10. So, cool, thank you. I was going to ask if you can hear me, but I guess you can. All right, so yeah, hopefully this is our last remote class for the school year. But there were people spinning out in front of the house at 5 in the morning, so I think I made a good call for myself. So things are melting. Presumably by Wednesday, things will be clear enough to get back to the classroom. But for today, I decided just to call it last night and go remote, just to avoid last minute changes and such. So we'll do this one more remote class today. And hopefully the other half of the class got the word and shows up. There we go. All right, so let's see. First things first, SLP upload is due tomorrow morning. Please upload your poster by then. I will send the posters to the printer tomorrow afternoon and have hard copies available for you next Tuesday for the Project Expo. If you don't get it uploaded by tomorrow, then you're probably on your own as far as printing it. If you want to have a copy of your poster to show to people and talk about. The template is available in the assignment, so just download that and fill in the sections. And the hallway in the STEM building going down to the Nerd Cave is covered on one side with posters from past years. So those are good examples also. There's also, yeah, I don't think they have them on the engineering website, but they're hung up in the STEM building. Cool, you're welcome.
What needs to be on this poster?
Take a look at the template in the assignment. It outlines each of the sections. I mean, we can do that right now. Let me log in off screen here.
On the ENGRCS website, under the ECS Club, there is an example.
Yeah, there's 3 templates, and I want to make sure I point people to the right one, which is the one listed in Canvas, because there is a slightly different template for fall when we do this in fall, and for winter, and sometimes there was one that we required for spring. So I tried to post the precise one in here. So let's just grab that one. I'm spending a lot of time waiting for Canvas lately, so this is a new aspect of my life. Maybe less full screen. Maybe down. Oh, there we go. All right. Project title is self-explanatory. If you don't have a fancy title, just put something in there. Put in today's date. If you're taking this from an earlier piece of work you did a year ago, at least update the date to today's date. You don't need a team name, but you can have one if you want. But I'd like the full name of everybody involved in the project. No initials, please. Full first and last name. If it's just you, just put your name there. And then the main sections to think about putting in, and you can change this as you see fit, but you know, problem definition, somebody's going to come up and look at your poster. They know nothing about you. They know nothing about what you're working on, what your project is. So some sort of synopsis of what it is that you're trying to do. So, you know, problem statement is probably the main piece here. Just a 1-sentence, 2-sentence description of what you're doing. This is kind of like your elevator pitch. right? So who here is familiar with the notion of an elevator pitch? So elevator pitches, right? You're in a building somewhere and you're riding the elevator, and just before the door closes, um, Jeff Bezos walks in and hits the 30 button, right? And so he's riding up 30 floors with you in an elevator. There's nobody else in there. You have, 20 seconds, 30 seconds of this person's attention, right? And you've got some really cool project that you're wanting to work on, but you need financial backing. You need somebody to support this project, right? And now you've got the audience with this person, but only for, half a minute. So how do you describe your project to this person in 30 seconds in such a way that when they get to their floor, they're going to, give you their phone number and say, give me a call, I'd like to hear more, right? So elevator pitch is what's the synopsis, the boiled down idea of your project that really sort of grabs someone's attention, describes the essence of what you're doing. So, I mean, think about elevator pitches. It's a really good way to characterize something that you're working on. And you can put that up here in the problem definition. And then some other things you can put in here. What's the scope of the project? We always want to be cautious of scope creep, where, we're going to do this, but we start doing all these other things because we're engineers and we like, adding more challenges to our work. So if you can narrow the scope and specify exactly, how far is this project going to go. Schedule, this is where you can talk about milestones if you want, or more generally, when do we expect to have certain major pieces done. Resources, time, other people, support from other entities, money, things like that. So that's your problem definition, probably the most important piece of this. And this is expanding on what you came up with in your original project proposal in the beginning of the quarter. And then competitive analysis, this is just basically, if this is not something that is completely novel, which it probably isn't, it's probably something that, already exists in some form, just sort of think about, what are the pros and cons of this. We're not expecting you to be commercially competitive with, every other entity in the marketplace, but just kind of, do some brainstorming and what are the advantages of this? The main advantage may be that this is something that you're creating, right? And you control all the source code and you know all the parts and pieces of it and so on. Potential applications, so, whatever, depending on your project, this may or may not make a lot of sense to include. Future improvement ideas, beyond, this quarter and next quarter, when the SLP finishes, where could this go down the road if you wanted to continue it after your time at Clark? And then this half is basically, what you've done this quarter, as far as moving towards implementing whatever it is that you're working on. So your solution specifications. And this can be whatever form makes sense. It can be text, it can be flowchart, block diagrams, pseudocode, up to you, right? And we don't expect you to have your project finished at this point. It's very possible that your project is only at the very start right now because maybe you've been trying to figure out the details of what you're going to do. But you should have some idea at this point of how you're going to do it. And so that's what your solution specification is. And that can, like I said, take whatever form you like. You can modulate this layout as you see fit, but we're trying to keep sort of a consistent look and feel to this. So, this at the top, the tag at the bottom, and a single page, bullet points or small diagrams and such. Does that make sense? Cool. All right, So that's due 8 o'clock tomorrow. And like I say, tomorrow afternoon, I'll take the ones that are uploaded and send them to the printer, and we'll get these 11 by 17 thin cardboard versions of these. And then those will be available for you next Tuesday.
Can you hear me?
Yeah.
Quick question. Can you kind of go over potential application one more time?
So let's say your project is what's the project I wanted to have the other day? I don't know. Let's say you're inventing Netflix socks, right? So those are socks that like monitor the motion of your feet, and when your feet stop moving, it decides you've fallen asleep, and it pauses your Netflix stream, so you don't have to figure out where you fell asleep. It's a real thing. So potential applications, right? Well, these could also be used for monitoring patients in a hospital bed, right? To decide when they fall asleep and measure how much sleep they get. Just kind of like, you know, if your project is geared towards one particular goal, right, you can just kind of think about, well, you know, suppose that this was, you know, my creation and I had a patent on it. Who else could I sell this to? Who else could use this, right? If I wanted to donate this to make the world a better place, who else would benefit from this? You can be creative in here, right? This is partially a marketing exercise. And it's an invitation to sort of think about what it is that you're working on from different perspectives.
Sounds good to me.
Cool, welcome. And so yeah, it doesn't need to be super fancy. I mean, if you follow this outline, these can all be bullet points, like I say. If you've got, you know, block diagrams or flow charts or things like that, you can put those in here. If you've got, you know, some sort of version 0.1 prototype that you can take a picture of, if you're building something physical, you can put that in here. But, you know, you're not graded on the slickness of this because we want everybody to follow the same format. So the most important thing is, you know, get this turned in with, you know, at least most of these sections included, whatever you think it takes to sort of present where the project is at this point. All right, any other questions on Service Learning Project? Welcome.
So this is more of a question of like me trying to figure out if I'm actually far enough ahead at this point.
Mm-hmm.
So this is more personal, but I guess it sort of pertains to everyone. So I'm currently like at a point with my project where it's kind of like I figured out everything I need to do,
Mm-hmm.
and I've gotten just barely started, as in learning the material, as in like I've gotten basically I'm using the stuff that I'm planning to use for something similar to the project, but much simpler, very, very basic.
Okay.
Like I've drawn a couple of pixels, really. That's what it is. It's more figuring out how the thing works. That was the hard part.
Okay.
But is that like part where I'm supposed to be? Because from here on out, it's mainly going to be me actually coding and creating the final project.
Right.
Is that a good point to be? Or?
Yeah, that's fine. I mean, wherever you are, that's where you are, right? So by definition, it's a good place to be. But yeah, I mean, a lot of the goal of fall quarter is you know, figuring out those kinds of details, deciding what exactly you're going to do, and what that looks like. And the way things look in the beginning of the quarter when you upload your proposal is not always the same as how they look at the end of the quarter when you've actually, you know, put in the time and gotten into the details. But you know, just write up your poster based on where you are and where you plan to go, basically. And you know, you have milestones in your proposal. You talked about what you wanted to do by the midterm, what you wanted to do by the end of the term. And so you know, if you met those, that's great. You can talk about that. If not, you know, adjust your milestones going forward, and and you can talk about, you know, what the timeline is from here out to June.
Okay, cool. So I won't have to stay up till 12 o'clock tonight trying to get a functioning prototype.
No, not at all.
Cool.
I mean, it might be nice to have something functioning by the exposition day, but
Yeah, so I mean, you have another week before you present, and you know the poster is sort of the thing that gets somebody who's walking by to come back and linger for a few seconds, you know, and see what it is that you're working on, and that's when you can say, hey, do you want to hear about my project, you know, and or if you've got, you know, something physical to show, you can like use that. So we used to call these dog and pony shows in the government, and like I mentioned before, they're called poster sessions in tech conferences. It's just, you know, an example of a way to sort of present your ideas to an audience, and it's a opportunity to practice selling yourself and selling your ideas, and that's a really useful skill. Yes, you can absolutely invite people to the presentation. Izad sent his one campus-wide email of the quarter yesterday, inviting people to the presentation. And yeah, more the better. We like people to come from wherever and just kind of see what students are working on, because there's a lot of really cool projects, and I know people are working hard on these, and it's great to get some publicity and let people see what students are capable of doing. So yeah, invite anybody you like. This will be our first in-person presentation since COVID, so that'll be nice to get back to. All right. Yeah, so chat question. Yes, PA4, you can work with people from the other section. PA4 is a group project. And if you want to work with someone in the online section, that's totally fine. All right. Yeah, you're welcome. So PA3 is graded, and you have comments and feedback on that. And PA3, really good job. A large number of people completed the assignment and had it working perfectly, including the delete function, including no memory issues, which is great. If the delete function was not working, I tried to grade the other parts of it, ignoring that, and in many cases everything else worked fine. And that was my suggestion, was leave delete for the end. Places where troubles came up were mostly minor things. So implementing a different delete algorithm than just replacing the root with the largest node from the left popped up a few times. Minor issues with the order in which things are done. For example, when you're here's the biggest node, here's the parent, here's the child. You know, the parent needs to adopt this child on its right, but in some cases people changed B to point to the root's left child, and then said, okay, parent, adopt B's left child, which makes B a pointer to the new root's left child and creates circles in the tree. So I saw that happen a few times, and the way to avoid it is, you know, have the parent pick up B's left child first and then change B's left child to be the old root's left child, and so on. A few issues with, you know, using equals to copy a string instead of string copy. And, you know, you can't say S2 equals S1 and actually copy the string. S2 equals S1 makes S2 point to whatever S1 is pointing to. But if I build a node in a tree, and here's my, first name, and I say, first name equals this thing, well, this is pointing to something in memory. And if later on I make another node and I say, okay, that thing should equal this, I end up with all of my nodes having their license plate point to the same location in memory. And the same with the first name, the same with the last name. And in this case, when you look at your tree, you see 1,000 instances of the same plate, first name and last name, right? And it's just this thing about C that we can't copy strings by using equals the way we do when we want to copy an integer value, for example. You have to use string copy. And string copy is kind of a backwards function. It takes a destination and then a source. And the other version of this that I don't think anybody do, I saw some of this during the time people were working on PA3, but I don't think I saw it in anybody's final, is you can't compare strings with double equal. You have to use string compare. And string compare, remember, returns positive, negative, or 0, depending on whether the first thing is bigger than, less than, or equal to the second. One thing I can mention is that when I saw errors in people's code, a lot of times those errors would have come up in doing some testing on the final code. For example, in some cases the comparison was backwards in the delete function. The recursive version said, if the plate we're trying to delete is smaller than the root, but then the code said delete it from the right subtree. And it's not in the right subtree, so the delete doesn't do anything. And that missed people's test, right? And so when I was grading their code, what I saw was the delete function doesn't actually delete anything unless you're deleting the initial root of the tree. And that's something that would jump out at you with some more aggressive testing. And so I can give you an example of how I tested your code. So this was the test script I used to drive my tests. But it generates a bunch of output, and I look at that output myself and check its correctness. So I run the make command twice, and the second one should say everything's up to date, and then I do a clean and I say make, and that should recompile everything, and the second make should say everything's up to date. And then I tried running it with a non-existent database, and that should give me an error, and most people had that working perfectly, so that's great. And then I ran it on the big database, and mostly just wanted to see, with 1,000 entries in the tree, can it look up some plates that exist? Can it respond to a plate that doesn't exist? And then I did a dump to make sure that the balance and the height were fine. And then I tried deleting a few plates and dumped again. I tried deleting a plate that didn't exist. And then I ran it through valgrind, and here the goal was just to look for memory issues. And so there should be no warnings from valgrind, and at the end it should say, all blocks freed, no leaks are possible. And then I did a series of tests on a really small database with just 3 nodes, C, B, and D. So this is just a nicely balanced tree of 3 nodes. And dumped it out, and then looked for each of those 3 nodes, looked for a plate that didn't exist, deleted the root, dumped it out again. And then I made a database with a chain of nodes, so this was just a chain going to the left. and dumped it out, and then deleted the root. And then I did the same chain and deleted a leaf, and then I did the same chain and deleted a middle node. And so that was testing, you know, the edge cases and then a typical case. And then I ran a different database here, DVC, so this is another nicely balanced tree. Sorry, it's not a balanced tree, it's a skewed tree, like that. And I tried deleting the D, and if I delete the D, it should be replaced by the largest node on the left, which is a C, and so the C should go up here. And so you should end up with a CB, so that was another test. And then I did one more delete algorithm test, which was this funny shaped tree. And so I'll draw this and then move it out of the way. This is an F, and then a G, and then a B, and an A, and a C, and an E, and a D. And then I tried deleting the F, and so here the F should be replaced by the largest thing on the left, which is an E. So this will become an E, and the C should adopt E's left child, so that D becomes the right child of C. And so this is testing all the pieces of that general case for the deletion algorithm. And for each of these, you know, I dump the tree before, I delete, and then I dump the tree after. And I you know, had a printout of what I should see in the dump before and after, and got really good at looking at those. And then for the last test, I did a grossly unbalanced tree, which is this thing. So a tree that looks like this. And so the left and right subtrees have the same height, but the tree is not balanced because this left subtree is not balanced. And so that was an easy way to check the balance algorithm. And again, you know, some people only check the heights of the subtrees. Some people only check to see if the subtrees were balanced. The balanced algorithm requires all of those things to be true. Left and right subtrees have to be similar in height. Left has to be balanced, right has to be balanced. So the moral of the story there is, right, aggressive testing. Exercise your code as thoroughly as you can imagine. Oh yeah, and then after those, I go ahead and look at the source code, and that's the testing I did. So that's a set of tests that I ran, you know, 40 some times. And it's helpful to have you know, a bunch of test cases that you can use when you're developing. And you know, remember from 224, you can do things like this. You can type in a command less than and put in a tag, and then have a bunch of input and then have that same tag. And this says, hey, run this command with these command line arguments and take everything between here and feed that to standard in. So you can make yourself a script that contains the input you want to feed to your program. And here I was just running the output through more in case it, you know, took more than one screen to show. And, you know, as you're developing code, especially when you're tracking down bugs, it's useful sometimes to have scripts that you're using for testing. And, you know, you might have multiple scripts. You're working on the search function, so you might make a search driver and just keep running that over and over and over again. And then when you think search is working, go ahead and add more stuff to it. and then do another one for, you know, delete, and so on. And this is nice, especially, you know, after you finish your code, and if you put comments in afterwards, after you've got the comments in and you've uploaded this, right, go ahead and download the tar file from Canvas, push it to the server, untar it, run the make command, and then run your tests again, and make absolutely certain that it's going to do what you expect it to. And yeah, someone just mentioned in chat, yeah, it's useful to test your functions as you go. If your code works perfectly and now you're adding the traversal code and suddenly, you know, something is breaking, well, it's probably related to what you just changed. And especially if you're using Git, you can go back and you can actually compare and see what's different from the version when everything seemed to be working to this version. And, you know, maybe you put a comment in that that broke something. You know, maybe you added a debug statement as a print and you forgot your curly brackets. And, you know, in C, if you say if blah do something and you don't have curly brackets, right? Well, if I add another thing in here, this is what gets executed conditionally. This gets executed unconditionally. And so sometimes making these nominal changes to your code end up, you know, making large changes to the logic. So testing your code is definitely a thing. Now, when you're in industry, right, a lot of times there's something like a QA department, and you're expected to test your code and, you know, have good confidence that it's working, but your code gets passed off to another group, and part of what they do is they really exercise your code to make sure that it's working correctly. But the more you can do that yourself, the better your experience will be. Any other questions, comments, thoughts on PA3? So that was a 150-point assignment, and take a look at your comments in Canvas. Right, I posted comments with what the individual deductions were for, as well as some additional comments in some cases. And if you're not sure what happened with your code, please come by office hours, and let's look at it and figure out what happened. All right, any questions on PA4? You should have everything you need for that. Let's see, for PA4, does it matter for the maxval function that we return a struct pointer instead of an int? It's probably important that you return a struct pointer instead of an int. You can do an int just to find the maximum value itself, but if you want to return the actual inventory, returning a pointer to a structure is probably the way to go. So I'd say that's exactly what you want to do. Yeah, so question about the dynamic programming part. So yeah, our function takes a single argument, possibly. Maybe it takes, you know, the inventory and stuff like that, or we can have globals or whatever. But the abstract maxval function basically takes a capacity and returns, let's just say for now it's returning an int. It'll be a structure that tells you how many of each item you have. But for the simple case, takes a capacity, tells you how much the largest value is you can get from that bag. And we can note the following. Our capacity is between 0 and 1024, because that's constrained in the assignment. And the maxval is always greater than or equal to 0. So those two things tell us how we can add the dynamic programming piece. we need to remember the solution for whatever capacity we have. Well, since our capacity is an int between 0 and 1024, we could make, you know, an integer cache bracket 1025. So now we can index this with values between 0 and 1024 and initialize all of those entries to -1. And a reason to initialize those entries to -1 is that we know -1 is never going to be a result we get from maxval. So if we look in our cache and we see a -1, we know that we didn't get that value from maxval. It's an uninitialized entry. So now in the beginning we can say something like this: if cache bracket capacity is bigger than or equal to 0, just return that cached value. No need to do any recursion. Otherwise, do stuff. Go through the long recursive process, find the answer, and at the end we're going to return the answer. But before we do that, let's save it. So where do we save it? Save it in our cache, indexed by the capacity. And then return it. So the next time we call maxval with the same capacity, this check up here will say, oh, I've already got an answer, and it'll just return it from memory. So that's the dynamic programming piece. Yeah, go ahead.
So we still have a function at all that takes arguments with like an array of values, an array of weights and stuff, or is that all just like completely unnecessary to be in the function definition?
So to do your stuff in here, you need to have an array that I've been calling an inventory. So it's an array with, you know, something like an item number, weight, and a value. And you can, so you need to read this from a file, so that's going to happen in the very beginning of your program, right, before you call your maxval function. You're going to open up the database file, read in each line, parse it, build up this either set of parallel arrays or an array of structures, close the file, and you have an option. You can either make this global or you can pass it as an argument to the maxval function. I'm okay with this being a global, but you could also make it an argument to maxval.
Okay, because yeah, I'm most of the way through P4, I think, but there's a couple things that are really tripping me up, and it might be because of the way I'm defining it, because I am defining it with those arguments.
Okay.
And then it feels like I would be able to continuously call it in an effective way with some of the arguments. So I think I will probably end up just switching to this then, I guess.
Okay. Are you trying to determine the particular set of items that give you a maxval, or are you only trying to do the maxval right now?
Well, right now I'm trying to get good output from it, but I haven't really gotten the saving the actual items individually.
Okay.
Trying to keep that in the back of my head to make sure I design around it though.
Good, good. Yeah, so my suggestion is don't try to do the list of items up front. Just try to get the integer maximum value out first. And you may feel like you have to go back and redo the whole assignment to add the extra items, but it will not be as bad as doing the whole assignment twice, right? If you can get this working with just an integer return value, that will get you through the dynamic programming piece, the recursion piece, all of those details. It'll get you your inventory ingest, your command line argument processing. You really get most of the project done, even if you have to go back and change the way that you return a value or the arguments that you take and so on and so forth.
Alright, thank you.
Yeah. Let's see. How do you initialize an array of structs so that each member is set to -1 with a for loop? No need to be fancy. You can initialize integer arrays when you declare them, like this, but you can't do that for anything other than 0. At least it's not guaranteed, unless you list out, 1,000 -1s. And for structures, it's even harder. Just make a for loop, just in the very beginning, and just iterate through your array and set things to -1 as you like. Alright, and again, if you want to work with somebody from the other section, that is totally allowed. Just coordinate it amongst yourselves. Alright, any other questions on PA4 or anything else? We talked about tries last week. And a number of dynamic programming applications.
Could you go over how to traverse a try one more time?
Sure. So with tries, remember, tries are these really wide arrays. These really wide nodes where we have say 26 pointers, one for each uppercase letter, and then we have this string at the end, this bit at the end that I'm calling end of string, and each of these points down to, another node, and those might have pointers to other nodes, and so on. And the quirky thing about a try is that the data is not actually stored anywhere in memory. So let me pull out my example from last week. So if you want to store a cat, we'll take the C, we'll point to another node for our A, we'll point the A to another node, and our T will point to a final node, and we'll set end of string to 1. And if we want cab, we'll take a C, we'll come down to A, we'll take the B, and point to another node. That's not right. We'll take the C, we'll point down to here to an A, and down here we'll have the B point to another node, and that'll set an end of string. So there's a try containing a cat and a cab, and so to traverse, to visit each node is pretty simple, right? It's just our regular traversal algorithm, but with 26 children instead of 2. And so we can go through all 26 pointers, and if we find something that's not null, we could just say, hey, traverse the try, starting with this node as the root. And when we traverse this, we'll see there's not a null here, and so we'll say, okay, first let's traverse the try with this as the root, and this will traverse everything that B points to and everything that T points to. But if we wanted to actually print the contents of the words corresponding to each end of string, that just takes some housekeeping, right? So
It's exactly like traversing a binary tree, except instead of 2 recursive calls, we need 26.
right. So you make a loop, right? Your pointers would be an array of 26 pointers, and you go through that. But the trick is that if you want to actually print the word that's stored at each point in the try, you need to do some remembering. So when I follow this third pointer, which is a C, I'm going to call my traverse function with this as the root of my try, but I'm also going to tell it, hey, any words that you find in here, prefix them with a C. So I'll pass a prefix to my traversal function, and each word that my traverse function finds starting from here will get printed with a C in front. And so when I come off the A, it'll make a recursive call, and it'll say, hey, each word that you find using this as the root, print it out with a prefix of the prefix I got, C, plus this letter A. And so this would print a cab and a cat. It's a fun thing to code. It's not that much code, but it's interesting to try to get this just right and store some data in here. It's a good exercise. Forgetting to tag my stuff ahead of time. But anyway, that's traversing tries. All right. Yeah, let's talk about the maxval function again. And let me pull up a worksheet I've made. Hold on one sec. Dynamic programming. There we go. All right, I'm going to print out a worksheet. We'll work through a maxval example. So our basic goal is we've got an inventory of items. So let's have an item number, let's have a weight and a value. I'll index from 1 just to make it interesting. So let's suppose this item weighs 2 and has a value of 5. This item weighs 3 and has a value of 8, and this item weighs 5 and has a value of 15. All right, so our algorithm is, we'll forget about dynamic programming for now. We'll just look at the algorithm itself. We have a choice of a first item that we're going to put in. Right, so if you start with item 1, we get $5 from having that item in our bag, and the remaining space in our bag is capacity minus 2. If we start with item 2, we get $8, and our bag now holds capacity minus 3. And if we start with item 3, we get $15, and our bag now holds capacity minus 5. And so we know that one of those is going to be a best solution. And so we simply calculate the final value we get out of each of those 3 situations. So we can say for item equals 1 to 3. And we can say this value equals value of our item plus whatever we can get out, in other words, the maximum value that we get from taking the capacity of our bag minus the weight of our item. And this is the thing to try to understand clearly. Right? So if we start with item 1, we get the value of item 1, we're left with a bag that holds the original capacity minus the weight of item 1. And from that remaining space in the bag, this is the maximum value we can get. And so if we add that to the value of item 1, this is the value we get if we start with item 1 in our bag. And so we can record a best value, and if this value is bigger than best, then just remember it as our best, and do that over all your possible items, and then return best. So if we spec this out, let's solve our maxval problem using this. Let's find maxval of 5. So our capacity is 5, and we want to find the maximum value. So this will be page 1. And we'll have to remember this inventory of items. We'll go back to it periodically. So we have 3 possibilities, right? We can start by putting item 1 in our bag first. So what's the value we get out of that? Well, item 1 has a value of 5. And the weight of item 1 is 2. Our capacity is 5, so if we put in item 1, which weighs 2 pounds, our bag has a capacity of 5. Now we have 3 pounds left to get maximum value out of. Let me fill these in. So we'll make this recursive call, while we're working on item 1, but let me fill these in, and then let's figure out what these recursive values are. If we start with item 2, we're going to get a value of 8, and a max val of 5 minus 3 is 2. And if we start with item 3, we're going to get a value of 15, and a max val of 5 minus 5 is 0. And so our main call to maxval is going to do these 3 calculations and return whichever one is the largest. So first it has to calculate maxval of 3. And that's going to be a recursive call. So how do we find maxval of a capacity of 3? Well, if we put in item 1, that gives us $5. And item 1 weighs 2 pounds, so we have 1 pound left. If we put in item 2, that gives us $8, and since it weighs 3 pounds, our remaining capacity is 0. And if we put in item 3, that weighs 5 pounds, our capacity is only 3. We cannot put item 3 in our bag. So remember, we need to do a check, if this is legal. So in this case, item 3 weighs more than our capacity. We're not going to calculate that. So now we need to calculate max val of 1. And so we'll make another recursive call. Max val for a capacity of 1. Well, if we put in item 1, which weighs 2 pounds, well, that weighs too much. We can't put in item 1 or 2 or item 3. We're just going to return our initial best value, which is 0. So max val will be 0, and our inventory will be, don't put in any of any item. It doesn't necessarily do every combination of items. I don't think. You could do that, right? You could do this by just iterating through all the possible combinations of items that fit in the bag, but I don't think this will actually do that much work. Because we're calculating these maxvals on demand. And I don't think we'll ever calculate maxval of 4, for example. Alright, so maxval of 1 is equal to 0 with an inventory of 0. And so that's a value of 5. And since maxval of 0 returned an inventory of 0, 0, 0, but we're getting this maximum value of 5 by adding one of item 1, we're going to change this to a 1. So we're going to take the inventory that we got for our maxval, and we're going to bump up one of the counts. In this case, we're adding item 1. We're going to bump up the count of item 1. And then maxval of 0, well, if the capacity is 0, we're not going to be able to do any of these. Our final value will be 0. Our inventory will be 0. So maxval of 0 is 0. This gives us a capacity of 8. Our inventory from maxval of 0 was all zeros, but here we're adding one of item 2, so we're going to bump up this count to be a 1. And item 3 we did not even consider. And so what's our maximum value? It's what we get by putting in item 2. And the max value we're going to return is an 8, and the inventory that gets us that is 0, 1, 0. Alright, so we have finished the calculation of maxval of 3. Maxval of 3 is 8, and the inventory is 0, 1, 0. And so 8 plus 5 is 13, and to get this 13, we take that inventory that got us maxval of 3, and we bump up the count for item 1. So there's the inventory of items that get us a maxval of 13. One of item 1, one of item 2. And I think we can make quick work of this last case. We need to find maxval of 2. So if the capacity of our bag is 2, well, we can put in one of item 1, which gets us $5 plus maxval of 0. And maxval of 0 we already calculated was 0. There's the inventory. So 5 plus 0 is 5. And we have to add one of item 1, so this becomes a 1. Item 2 and 3 don't fit, so we don't even calculate those. So our maxval will be 5, and our inventory will be 1, 0, 0. So we can return from this recursive call, which told us what maxval of 2 was. So maxval of 2 is equal to 5, and the item count that gets us that is this. And so if we start with item 2 here, 8 plus 5 is 13. And we get that by bumping up the count of item 2. And maxval of 3, well, we found, maxval of 0 is 0. So if we start with item 3, we get a 15. We bump up the count of item 3, it looks like this. So there's the 3 values that we'll get inside our loop. And when we're done, we'll see the max value we got was for adding this third item. So the maximum value for capacity of 5 is 15. And the inventory that gets us that is 0, 0, 1.
Is this worksheet available to us anywhere?
Yeah, I can post it. Alright, so now we look at this and we say, what's the final maximum value that we have? It's the largest of these. That would be this one right here. Max value of 5 is 15. We get it by putting in 0, 0, and 1. That's not right, though. Oh yeah, that is right. That is right. Yeah, so that's not a terribly interesting solution because it's a greedy solution. But anyway, that's the iteration through the recursive calls that go along with this sort of higher level view. I will put this under resources. All right, have fun with that. All right, does that make sense?
Assuming we fill out the worksheet correctly, we can use that to test our PA4 to like make sure we're getting the right output, right?
Yeah, you can, but you can also use the sample code if you want to try more complex cases, because this is really painful for more than the simplest cases. And you can do a more bare bones version of this by making a recursion tree. So maxval of 5, and this could be maxval of 5 could be 5 plus maxval of 3, 8 plus maxval of 2, and 15 plus maxval of 0. And maxval of 3 is 5 plus maxval of 1, and 8 plus maxval of 0. And you can draw it out in a tree like this, and it's a lot easier, I think, to do it like that. But using these worksheets lets you actually kind of trace through the way the recursion winds up and then unwinds. But for checking your answers, this works pretty well too. But then, like I say, also the sample code is a good go-to. So if you want to make an array, length 100 of strings, length 33, would it be char strings 33, 100? So if you want an array of strings, I think you would do it like that. So it's 100 strings of 33 each. But multi-dimensional arrays are kind of funny in C and other languages, right? I mean, we don't really have arrays, we have pointers. And my strong recommendation is make a structure right? Make a structure for each item, and now you can make, you know, struct item cache bracket 1025, for example. Or when you're building up your inventory, struct item list. And now you just have an array of 100 of these things. And you can do item list bracket index dot value dot weight or dot name. Yeah, I think that'll be simpler.
So when you say make a structure for each item, do you mean like as we read in the file, like each item in that file gets its own structure?
So you have one structure, right? And if you make an item list, which is an array of these structures, then each line you read from the file goes into the next element of this array. So read a line which will give you a name, a value, and a weight. Store that in item list bracket 0 dot name dot value dot weight. Read the next line, store it in the elements at index 1, and so on. And then you have just a single array that you can pass around that contains all 100 names, weights, and values. I don't think that works for the cache, but for your inventory that you read in from the file, that should work well. All right, other questions, comments? All right, well, let's talk about sorting. This is probably the last major topic for the course. We've got some other things we'll pick up along the way between here and the end, but this is the last sort of big separate topic by itself, is the business of sorting. So we're going to work with integers largely, but sorting is a more general problem. It's this question of organizing information in a computer in a particular order. So it could be alphabetical order, which is still really numeric, right? If we convert our characters to ASCII codes, we can think of a string as just a big long integer, but sometimes there's differences when we're sorting things in the way we sort things in English. But we're just going to work with integers. And so, for example, suppose you have an array of integers like this. And our goal is to rearrange them, presumably, you know, from smallest to largest or largest to smallest. And there's a lot of different ways we can do this. So this is a really old problem. It probably goes back to the late 1800s with the old Hollerith machines. But it's a fundamental question. And there's lots of ways to sort. And we're going to do a pretty high-level pass over a number of different sorting techniques. When you do an algorithms course, you'll dig into these in a lot more detail. You'll dig a lot further into the analysis of efficiency, best case, worst case, average case, and look at edge cases and so on. We're not going to go that deep. We're going to try to go through several different types of sorts and mostly sort of compare them to each other and look at general orders of complexity. So kind of typical case. And we'll start with the bubble sort, which most people are familiar with. I think we do this in 121. But we'll use that as a starting point of an example of a fairly inefficient but relatively easy to code sort. So let's do a 5-minute break, and we'll come back and we'll begin with that. So let's come back at 11:10. We'll come back in about 4.5 minutes. All right, so I'll see you in a few. All right, we're back. All right, so let's start with bubble sort. And who can recall the basic behavior of a bubble sort? What?
I'm pretty sure if I remember correctly, the basic behavior, you take the first one and the one after it, and then you see which one's smaller and you put that first, and then you increment by one, you repeat the same process.
Mm-hmm. Perfect. So we start at the beginning, we compare the first number to the one after it, and suppose we're going from smallest to largest. So if these two are in the wrong order, we just swap them. And now we repeat, the 20 and the 4 are in the wrong order, so we'll swap them. And this will become a 4 and a 20. And the 20 and the 16 are in the wrong order, so this becomes a 16 and a 20. And 20 and 30 are fine. 30 and 5 are in the wrong order. 30 and 11 are in the wrong order. And 30 and 3 are in the wrong order. So our final result after this one pass is an 8, 4, 16, 25, 11, 3, and 30. And a lot of things moved around, but the one thing we know is that the largest number is now at the bottom. So yeah, this is how people would sort themselves by height. Exactly, you just look at the person next to you and swap places as needed. So one pass, one sweep through the data moves one number into its correct spot. In this case, the largest number goes down to the bottom. And we can repeat this. It's not recursive, but it's iterative. We can repeat this and make a second pass. And if we made a second pass on, this upper set of data, presumably the 20 would end up down here. And so after two passes, we would have two numbers in the correct spot. And so if you have n pieces of data, it takes you basically n passes to sort the entire set of data. And if we think of each pass as moving from the beginning to the end, each pass takes n operations. And so this is where we're doing this order of n business, where we're sweeping aside details. For example, as we go through, we're doing n operations, but sometimes those operations involve just comparing two numbers. Sometimes they involve comparing numbers and swapping them in memory. So this operation is not always the same length, but it's pretty close, right? It's close enough that we're just going to say that as we go through one pass, we do order n operations. And similarly, we may note that, the first pass we had to go through the entire set of n pieces of data, but once we have this 30 in the right place, our next pass is actually shorter. We only have to go through n-1 operations. And that turns out to be a constant difference in the total amount of work we do. So, rough calculation, n passes, n operations per pass, this is order n squared. If we get fancy and we reduce the size of each pass, it's roughly n squared over 2. But order of complexity, that's the same as n squared. So bubble sort is an n squared algorithm. And that's not great. You wouldn't want to sort a billion pieces of data with a bubble sort. But for, a small set of data, 1,000 elements, it's not a bad performance. And there's other things we can do. For example, if we note how many times we swap as we go through, and we complete a pass and we did not change anything, we know that we're done, right? If we never swap anything, it means each number is smaller than the number after it, our array is sorted. So we can actually get away with fewer than n passes by putting in some logic. And so best case, right, we might have much fewer operations. But this is on average still an order n squared. So is everybody okay with the basic behavior of bubble sort? All right, so the next pair of sorts are also order n squared. And these are called insertion sort and selection sort. And they're similar to each other, and they can get confused pretty easily. So I'll give you the memory mnemonic that I use for keeping track of which is which. So let's talk about selection sort first. And I may as well stick with our same set of data. So we'll go with 28, 4, 16, 35, 11, and 3. All right, so selection sort. Significant video lag. I don't know what I can do about that. I can close out Canvas. I can close this. I can close this. I think that's all I can get rid of. Alright, if the lag gets super bad, let me know. I am recording this, by the way, and I'll post the recording after class. So, hopefully it's workable. Alright, so selection sort. This also makes n passes. And each pass select smallest element and place in the output. So here's our input and here's our output. And so we're going to go through our input n times, 8 times in this case. And each time we go through, we're going to pick the smallest element we find that we haven't already selected. And it's pretty easy to go through an array and find the smallest element, right? You start off with your first element as your smallest. Then you go to the second. If that's smaller, you remember that is your smallest. So 20 is our first smallest. And then we'll come to an 8 that's smaller. There's a 4 that's even smaller. 16 is bigger, 30 is bigger, 5 is bigger, 11 is bigger, 3 is smaller. We're at the end, that's it. 3 was our smallest number. So we're going to copy that into our output array, and we're going to somehow tag this to say, hey, we've already taken out that 3. And now we're going to do this again. We're going to start with a 20, 8 is smaller, 4 is smaller, 16 is bigger, 30 is bigger, 5 is bigger, 11 is bigger. Hey, 4 is our smallest number. So we'll add that to our output array, and we'll tag that. And we're just going to keep doing this. Start with a 20, 8 is smaller, we've already done a 4, 16 is bigger, 30 is bigger, 5 is smaller, 11 is bigger, 5 is our smallest number. We'll add that to our output array and tag that. So super straightforward, right? Each time we go through, we pick the smallest number we haven't yet picked, and we just keep adding those selections to the output array. And so I remember this as a selection sort because it's the selection process that's actually doing the sorting, right? We're selecting the next thing that we want, so we're doing the work in the selection piece. Each of these sorts we can think of as we pull things out of the input, we place them in the output. So we select from here and we insert into here. When we're making our choice in the selection part, that's a selection sort. So what is the average order of complexity for this sort?
Well, I mean, wouldn't this be n squared divided by 2? Because the input gets smaller every single
Yeah.
time, but then again, the divide by 2 doesn't really matter.
Yeah, so this is still roughly an order n squared. If we could actually remove these from the list, our input would get smaller. If we're just tagging them for adding a flag or setting them to infinity or something, then we're still actually going through n pieces of input. And we do that n times, total of n passes. So this is still an order n squared. Any advantages to a selection sort over a bubble sort that you can think of?
There's less things to keep track of variable-wise, so I guess it'd be more memory efficient.
Yeah, there's less things to keep track of. There's a definite memory difference. In our bubble sort, when we make one pass, right, to find the largest number and put it at the bottom, look at all the things that we moved around in memory. Right? Really, all we wanted to do was put this 30 down here. But we swapped the 20 and the 8, and the 4, the 20 and the 16. We swapped the 30 and the 5, the 30 and the 11, and the 30 and the 3. We did a lot of memory reading and writing. And that can have a performance impact. Reading memory, pretty inexpensive. Writing memory can cause issues. Yeah, so someone said in chat, takes the same amount of time for sorted and unsorted arrays. Bubble sort takes forever if perfectly unsorted, but no time at all if perfectly sorted. Yeah, so if we had two arrays, input and output, right, the input array basically stays untouched unless we're setting tags in here to, mark something, but the order of the data is unchanged. Bubble sort is usually done on a single array in place, and so we're constantly moving things around. And if this is a really large array, writing data has performance implications in terms of caching your memory. That's a computer architecture discussion. And we can do a selection sort with a single array, where when we get to the end, if we decide that 3 is our smallest number, well, we could switch that with the first element, right, because we need the 3 to go in the first place, and so we could take that first number and move it to the end. And now we don't need to tag our data, we simply begin with the second element, and we search through and we try to find the smallest number, and if we find the 4 is the smallest, then we'll swap the 4 with whatever the second element is. And now we'll start from the third element, find the smallest, we find a 5, so we'll put the 5 up here, swap it with the 8. And so we can do a selection sort in place on a single array, and we end up swapping 2 pieces of data each pass, which is still a lot less than we might get with a bubble sort. So this will sometimes be better performance-wise in terms of how much it perturbs memory. Let's see, interesting. So is there a sort that tracks biggest and smallest with every pass? That would be a nice embellishment on this. As you're going through, track the biggest and the smallest. And when we're done, if we find 30 is the smallest and 30 is the 3 is the smallest, 30 is the biggest. We could put 30 up here, put 3 up here, and put 30 down here, and now work on a subset of data that has 2 fewer elements. I don't know what the name of that is, if it's named. Maybe that's pulse sort. I haven't encountered that, but that's a nice embellishment on this, and it takes almost no more work than a straight selection sort. All right, someone says video lag is less significant now, so that's good. All right, so that's selection sort. The dual to that is insertion sort. That's a little hard to say. Insertion sort. Excellent. All right, so we'll keep picking on. This is just my day for. That doesn't work. I already scribbled all over them. I was gonna say it's my day for ripping up my whiteboard. All right, so insertion sort. We again make n passes. Each pass, place next input number into proper place in the output. So we're going to have our input array, we're going to have an output array. And this time the selection is trivial. Each pass we just select the next element from our input. But in inserting that number into the output, that's where the sorting happens. So what does this look like? We start off, we take the first number as a 20, we put that in our output array. We select the second number, which is 8, and we put that into the proper place in our output array. So we'll put that before the 20. We select our third number as a 4, we put that in the proper place in our output array, so that's going to go before the 8. We select the next number as 16. It's got to go after 4, after 8, it should go before 20, so we put it right there. And we keep doing this, and when we're done, our output array is properly sorted. So does anybody remember coding this earlier this quarter? When did you do this in C? Yeah, this is how you did your linked list code. Right, our output was a linked list, and if your output looked like this, and you wanted to insert a 5, you started at the beginning and you moved down until you got to a number that was bigger, and then you inserted right before that. Right, so that was basically an insertion sort. And so again, one more time, the selection is trivial. We just keep selecting the next element from the input. But the choice of where to insert it, that's where the sorting is taking place. It's in that choice of where it goes in the output array. Alright, so we have to make n passes, and each pass we need to go through our output array until we find the correct place. If this is a linked list, we need to go down our linked list until we find where to insert it. And so nominally that's, roughly half the length of our output array, average case. And so this turns out to be also an order n squared. Again, it's like n squared over 2, but that's still n squared. if we're outputting in an array, this is potentially a lot of movement of things in memory. If we were outputting in a linked list, it's not a whole lot of memory changes, because we know that to insert something between 4 and 8, we don't have to change any of this stuff. We don't have to change anything back here. We just change this node's pointer to point to our new node. So not a bad memory impact. So when I was fully in person, you know, for most of my time at Clark, I got to wondering how I sort homeworks and exams when I'm grading them, because it turns out, you know, if I'm grading 35 exams, I was spending a lot of time just alphabetizing my exams so I could enter them into Canvas. So they get turned in a random order, right, based on when people complete. And so I have basically a list of 35 entries. And it looked like mostly I was using an insertion sort. So I picked the first name, you know, the first exam, and I put that in an output pile. And then I take the second exam and I place it either before or after that first one. So now I've got two things in my output. Now I take the third exam and I place it either before, in the middle of, or after those two exams. And so I'm building an output pile. And as I go through... Say again?
Is this more or less how we kept the trees in PA3 sorted?
Not exactly. So in PA3, it's a little different because we're bifurcating.
Yeah, but the idea is to insert things to the left or to the right. Or something.
Yeah, it's still an insertion kind of operation. That's true. So if I do this on, you know, 30 some exams, this ends up being, you know, like 1,000 operations, or at least several hundred operations I was doing just to alphabetize exams. And that had never occurred to me, right? But that was taking a big chunk of time. So some of these next sort algorithms that we go through are actually ones that I switched to using when, you know, sorting papers to put into a grade book and such. And so one that I actually use, and this is probably one of the funnest sorts to think about, is called a merge sort. All right, so how does a merge sort work? So I have a list of, I'll go back to numbers. I have a stack of 8 papers from students named 28, 4, 16, and so on, right? So I can do my insertion sort on a small stack of tests, right? I can take these first 4 and I can order these by doing something like an insertion sort. So suppose I do this and I get a 4, an 8, a 16, and a 20. And then I do the same thing on the second set and I get a 3, 5, 11, and 30. Alright, so I have 2 stacks of paper. I have 2 sets of numbers, and each of these is sorted. What I'm going to do is interleave these. Which means, you know, if these are actual stacks of paper, all I can see is which one is on top. Right? I see this stack starts, you know, with a 3 and this stack starts with a 4. So I take this one and I put that into my output. And now I'm looking at the second thing in this array, I'm still looking at the first thing in this array. Which one is smaller? It's a 4. So I'm going to put that in. And I'm going to move down. And now I'm looking at a 5 and an 8. Well, the 5 is smaller, so the 5 goes to the output. And now I move down. And I'm looking at an 8 and an 11, and the 8 is smaller. So the 8 goes in my output, and I move down. Now I'm looking at an 11 and a 16. So I'll put the 11 into my output and move down. Now I'm looking at a 16 and a 30. 16 is smaller. So that goes into my output. Now I'm looking at a 20 and a 30. 20 is smaller, so that goes to my output. Now I'm done with this list, so now I just take whatever's left in this pile, which is just a 30, and I add that to my output. Alright, is everybody on?
Correct me if I'm wrong, but wouldn't this take order n amount of time?
Yeah, so this takes order n to do this interleaving. But you still need to sort these half lists to begin with. But does everyone understand this interleaving process? If you have 2 sorted arrays, you basically just start at the beginning of each, and you repeatedly take the smallest, and move it to an output, and just keep doing that. And it's a little subtle to code. If these are my 2 arrays, right, I look at the 2 and the 5, I put a 2 in there. I look at the 4 and the 5, I put a 4 in there. I look at the 5 and the 7, I put a 5 in there. I look at the 7 and the 10, there's the 7. I look at the 8 and the 10, there's the 8. I need to recognize at this point that there's nothing left in this first array, and so now I just take all of these remaining entries from the second array and I add them to my output. If you're doing this with physical papers, the result is my first pile is empty now, so I just take the second pile and put it underneath my output stack. So this interleave operation is order n. And so we can define a merge sort. So this is pseudocode, so I don't have to write valid C. This takes some array of data, and it should turn it into sorted data. And here's how we're going to do this. We're going to say, you know, data 1 equals left half of data. Data 2 equals the right half of data. And if data's got an odd number of things, just make a choice. But, you know, roughly split it in half. And then we want to sort data 1, and we want to sort data 2 somehow. And then we want to interleave data 1 and data 2. Alright, so merge sort. Take your data that you're trying to sort, split it into 2 halves. I'm calling that D1 and D2. Sort each of those small halves, and then interleave them using this kind of process. And you end up with your sorted data. Make sense so far? Alright, so question, how should we sort these half-sized arrays? What's a good sort to use?
Did we just merge sort them?
Since I'm claiming merge sort is a better than n squared, let's use merge sort. Right, that's the recursive approach. So we split our data in half, we call merge sort on each half, and then we interleave the result. So we know the interleave takes order n. And the question is, how many times are we going to recurse? So we need a base case, right? If data is empty, we'll just return. If it's only got one element, we can return two, but you know, we'll make an extreme base case. If data is empty, we're just going to return. So the question is, if we keep splitting our original data in half, how many times do we do that until we get down to something that doesn't have anything in it? In other words, when I split this in half once, I'll have a list of 4. When I split it in half a second time, I'll be down to 2. When I split it in half a third time, I'll be down to 1. If I try to split it in half again, I'll end up with, you know, at least one of my lists being empty. So it looks like the number of times you're going to have to recurse is the number of times it takes to cut our list in half before we get down to a single element. And so what is that order of complexity? How many times you cut something in half before you get down to 1?
Log n.
Yep, that's a log n. So you can do roughly log n sets of recursive calls. And so merge sort turns out to be an n log n complexity. And this is our first sort that gets way better than n squared. So if n is 1,000,000, right, n squared is about 1,000,000,000,000. N log n is only 20 million. So it's not quite order n, but it's a whole lot better than n squared, especially as n gets big. And so this is a really efficient sort. On the other hand, it's a little more complex to code. But that's largely because of the logistics of dealing with arrays in C. In other languages, this is more straightforward to code. But trying to do something like split an array in half and pass around the left and right sides, and the fact that we don't even have a way to know how big an array is in C unless we pass around a length with it, makes coding this a little less pleasant in C. But algorithm-wise, it's very straightforward, right? Cut your list in half, sort each half with merge sort, and then interleave them. All right. Other questions about that? All right. Let's see. Oh, I forgot to tag that too. My tags are not on point. That's okay. All right. Let's look at a radix sort. So radix sort works really well for integers if we think of these integers as strings. And so let's imagine we have a set of 3-digit integers. And we want to sort these again from smallest to largest. So what we're going to do is a series of passes where each pass we look at only one digit of each number. And so our first pass, we're going to look at this least significant digit. And we're just going to sort our numbers based on that one digit. And so what we would like to end up with in the end is we'd like a 400 followed by 200, followed by 110, followed by 851, followed by 506, 247, 147, and 399. So sort by least significant digit. And the important thing about this is if two numbers have the same least significant digit, don't change their order. So for example, 400 and 200 both end with a 0. When I sort my data by least significant digit, I need the 400 to still come before the 200. So this influences what type of sort we're going to use. A selection sort would work well, an insertion sort might not work as well. But since we're sorting by digits, and we know there's only 10 possible digits, we can do this task of sorting by the least significant digit by making 10 passes through our numbers. And so here's our idea. Make 10 passes. Pass 0. Pull out anything that ends with a 0. Pass 1. Pull out anything that ends with a 1, all the way down to pass 9, where we pull out anything that ends with a 9. Alright, so let's try this. Let's go through here and let's look for anything that ends with a 0. Well, there's a 400, there's a 200, and there's a 110. Now we're going to make a second pass, look for anything that ends with a 1. There's an 851. Make a third pass, look for 3s, look for 4s, look for 5s. Pass 6, we'll look for anything that ends with a 6. There's our 506. Pass 7, we'll find the 247, and then the 147. Pass 8, we don't find anything, and pass 9, we find 399. And that's the end of our first pass. Second pass, we're going to go through and we're going to do the same thing, but based on this second digit. And we can do this the same way by making 10 passes. So first we'll look for anything with a 0 in this second place, and we'll copy it to our output array. And then we'll look for anything with a 1 in this second place. And then anything with a 2 or a 3. And then with a 4, we've got a 247 and a 147. And then a 5 gets us the 851. Nothing with a 6, 7, 8. And finally with a 9, we've got a 399. Alright, that's the end of our second pass. Now we're going to do one more pass where we sort by digit 3. And we're going to do that exactly the same way. We're going to make 10 passes through our data. First we look for anything with a 0. We don't find anything. Now we look for things with a 1. So there's a 110, a 147. Look for anything with a 2. There's a 200. There's a 247. Look for anything with a 3. That's a 399. Anything with a 4, there's a 400. And that's it. Anything with a 5, there's a 506. Nothing with a 6, nothing with a 7. And there's something with an 8, 851, and nothing with a 9. And guess what? Our data is sorted. So that's a radix sort. And if we store our numbers as integers, it doesn't work really well because it's really hard to find, you know, what the third digit of an integer number is, unless you get into lots of division and modulo and things like that. But on paper, this looks pretty straightforward, right?
Can we see the description of the engine?
Yeah. So to sort by least significant digit, if two numbers have the same digit, don't change their order when you do this. So we're just going to make 10 passes, take everything that ends with a 0, copy that to the output, then go through again, take everything that ends with a 1, copy that, and so on. And then repeat for second digit, third digit, and so on until you get to the most significant digit. All right, question. For 10-digit integers, how many of these outer passes do we need? 10. For each pass, how many times do you go through the data? Right? It's 10 times, right? Because we go through once to pull out the things that start with a 0, go through again to pull out the things that start with a 1, go through again to pull out the 2's, and so on. So we have 10 outer passes, one for each digit, and on each of those passes we have to go through our list of numbers 10 times, and each pass requires n operations. So for 10-digit numbers, this looks like order 100n, which is the same as order n. So this looks like an order n sort algorithm, which technically maybe it is, but it's not actually better than our order n log n algorithms. So this is a case where this order of complexity can be deceptive. If we have 10-digit numbers, that gets us up to, you know, a billion, a few billion, right? If we have 32-bit integers, and those integers are 10 digits, we know that our n is on the order of a billion, which means n log n is on the order of 30n. So we say we can ignore these multipliers when we look at order of complexity, and it's true. If n grows towards infinity, this looks like order n. But if n grows towards infinity, this is not 100, right? If n grows towards infinity, the number of digits in n is also increasing. And we're still only going to do 10 passes through our data in this inner pass, looking for zeros, 1, 2s, 3s, and so on. But this actually depends on the number of digits. So this is actually order dn, where d is the number of digits in our numbers. And as n grows, this also grows. And the number of digits is basically log n. And so this turns out to be some...
You also need to throw in, like, the number of unique characters for, like, per digit? Or is that not...
Yeah, so if we're working with integers base 10, this is a 10. If we were working with words with uppercase letters, this would be a 26. If we were working with binary data and we were doing this byte by byte, this would be 256. Because that's the number of possible bytes we could have. So we could use this to sort binary data, but this number would change. So on a rough calculation, this may look like order n, but in practice, it's not. It's not as good as many of our n log n sorts that we'll see. But it's still a fun sort to code. And this, I think, is sometimes called a Hollerith sort. And so if you have census data on punch cards, you can build a machine to sort using this approach. In case you're caught in a time travel loop. All right, questions, other questions on that? All right, so on to a quicksort. And I think quicksort is probably the hardest sort to kind of wrap our heads around. But we'll do a few examples of this. This is also not a bad one to code. And it's got some interesting performance characteristics. So let me make an array of numbers. And I'm going to put these out sideways. All right, so there's a set of numbers we want to sort. And again, we're going smallest to largest. All right, so here's how this works. So we're going to pick one number as the pivot. And usually this is going to be the last number. So I'm going to pick my 17 as a pivot. I'm going to underline it. Right? And I'll go ahead and label it. This is our pivot. And then our goal is, rearrange the other numbers into two pieces. Like this, where everything over here is less than the pivot and everything over here is greater than the pivot. So we're going to pick one number, usually the last thing in the array, as our pivot. And what that means is we're going to rearrange the rest of these numbers so that everything in the beginning of the array is smaller than the pivot and everything at the end of the array is bigger than the pivot. Definitely recursion. And we want to do this piece as efficiently as possible. We want to do this in an order n operation. And so we're going to have a pair of pointers. We're going to have one pointer pointing to the first number and another pointer pointing to the last number. These are just indexes into the array. And so we're going to start with the first number and move right till number is bigger than the pivot. And then at that point we're going to start with the last number and we're going to move left till we find a number which is smaller than the pivot. Alright, so what does this mean? Our pivot is 17, remember that. We're going to look at the first number as a 12. 12 is smaller than the pivot, so we're okay with this one. We're going to move to the right. Here's a 23. 23 is bigger than the pivot. And that means this is in the wrong spot. We would like this to be somewhere towards the end of our array. So we're going to stop there. So that's what this first thing is. Keep moving right until we find a number bigger than the pivot. Now we're going to start here with 19. And that's bigger than the pivot, so we'll move left, and now we find a 1 which is smaller than the pivot. Alright, so after we're done with this, we're looking at a number on the left which is too big and a number on the right which is too small. And so now we're going to say swap those. So we're going to swap this 23 and 1. And so now our array looks like this. Here's our 23, our 12, there's our 1, 11, 14, 60, 55, 8. The 23 came over here, the 19 is there, the 17 is still the pivot. And our index, we were looking at this number on the left and this number on the right. And now we're just going to go back up and repeat. So we're going to move over to the 11. 11 is smaller than the pivot, that's good. We'll come to the 14. 14 is smaller than the pivot, that's good. We'll come to the 60. 60 is bigger than the pivot, that's a problem. So we're going to stop there. And now we're going to move in from the right. So we're going to move over to the 8, and 8 is smaller than the pivot, that's a problem. So now we're going to swap these two numbers. And again, this number is too big, this number is too small. So we're going to swap those. So now our array looks like this. 12, 1, 11, 14. The 8 came over here, 55. The 60 came over here, 23, 19. 17 is our pivot. And our current index was here and here. And we're going to go back and continue doing this. So we're going to move to the right. And there's a number that's bigger than our pivot, that's a problem. And we're going to move to the left here. When we move to the left, we're pointing to the same number that we were pointing to moving from the left. And so we are done. Right? So we're going to repeat until two indices match. And so we found this number 55 in the middle. What we know at this point is that everything to the left of 55 is smaller than the pivot. Everything to the right of 55 is bigger than the pivot. Everything to the left is smaller than 17. Everything to the right is bigger than 17. So what we want to do is we want to take our pivot and swap it with this number that we collided with in the middle. And so now our array is going to look like this. So the 17 goes in place of the 55. And the 55 goes in place of the 17. And now I'm going to draw a circle around that number that was the pivot. So repeat until indices match. And then we swap that middle number with the pivot. All right. What we know about this new array is that the 17 is in the correct spot. Right? Everything to the left is smaller than 17. Everything to the right is bigger than 17. If we move 17 over, one of these numbers, which is smaller than 17, is going to end up on the right. And if we move 17 this way, one of these numbers, which is bigger than 17, will end up on its left. So at the end of this one pass of a quicksort, our pivot is now in the correct location in the array. If 55 was smaller than the pivot, then our first index moving would have accepted the 55 and gone over to here, and we would have noticed that we were pointing to the same thing that our right pointer was pointing to, and so we would have stopped here, and that would get swapped with the pivot. So this is easier to do on paper than it is to write in code. No doubt. But that's the basic main pass of a quicksort. And we don't do a lot of data movement. We do a few swaps, right? Each time that we get a pair of numbers that are in the wrong position, we swap them. And you know, that's going to happen sooner or later. And then at the very end, when our arrows are pointing to the same thing, we swap that number with the pivot. So what is the order of complexity of this main pass? This thing that we just did. Yeah, this is order n. Right? We're basically starting here, we're looking at this, comparing it to the pivot, looking at this, we're coming from here, looking at this, looking at this, looking at this. Somewhere we may do swaps. We might swap every time we move. We might never swap if you know, everything was already partially sorted. But we're going to end up doing something roughly n times. So this main pass turns out to be order n. And when we're done, we don't have a sorted array, but we know everything over here should be to the left of 17, everything over here should be to the right of 17. Now all we have to do is sort this array and sort that array. And everybody knows the answer. What's the best sort we can use to sort this smaller array? quicksort, there you go, right? That's the nature of the beast. So we're going to do one pass to hopefully split our array roughly in half, and then we'll do quicksort on each of these halves, and we're done. So again, just like with merge sort, we don't actually do sort, we just have to code up that interleave method. For a quicksort, we don't have to actually do any sorting, we just have to code up this moving of a pair of pointers, swapping things when they're out of order, and then swapping our final pointers locations with the pivot. And then we recursively call quicksort on the left and right pieces. And so this also turns out to be order n log n on average. All right, so we'll do another example of this on Wednesday. Hopefully, you know, like on the whiteboard in person. We'll do another example of this. We'll also look at what a worst case performance is for a quicksort. And quicksort can give you n squared behavior if you're unlucky. So we'll look at that and do some analysis.
So, quick question.
Yeah.
Why would you ever use this one if it could be worse or could be better than the other one, which we know is log n log of n as well? We can force this one to be n log n. It turns out if our data is sorted or close to sorted to begin with, this ends up being close to n squared. But if you're using quicksort, you basically randomize your data first, and then you get this nice n log n behavior. Okay, cool.
Yeah, you're welcome. All right, so we'll play more with quicksort. I'll probably have people work on it in class on Wednesday, because it's, like I say, to me it's a more obscure than a merge sort or, you know, selection insertion. So we'll play around with this some more. And then I want to talk about heaps and heap sort and implementing heaps and things like that. So we'll do those things on Wednesday and continue talking about PA3 as people want, or PA4 as people want, maxval functions and so on. And that will probably round out our sorts. And then depending on how much time we have left, week 10, we will pick up some other topics. We might talk about red-black trees. I want to look at some code for doing AVL trees to do those rotations we talked about, and some other things like that. So that's all I got for today. I will post this recording after class, and I will almost certainly see you in person on Wednesday. All right, so have a good one. I'll catch everybody next time.